In this tutorial, we are going to review a few questions on basic chemistry and introduction to stoichiometry. So some of the rules that apply in terms of significant figures, conversions, and also dealing with some oxidation numbers. Okay, let's get started. Okay, determine the number in milligram in 0.020 kilogram 10. So we've been given a number 0.020 kilogram. Now we need to convert this to milligrams. What do we get to understand? So there's some prefixes that you have to understand in chemistry and of course in any science. Basically, when you say a kilo, you're talking about a conversion to or multiplying by 1,000. Okay, so it's a 10 to the power 3. That is what a kilo stands for. So we have our conversion in grams. Then for milli basically gets to mean that 10 to the power negative 3. Okay, so basically we need to understand that 1,000 milligrams is basically equivalent to what? To a gram, because the milli that is attached to a gram is the same as what? Is the same as 10 to the power negative 3, which basically also means that when you're multiplying by a negative power, it's more like you're dividing by 1,000, so which is just be like equivalent to a gram. Okay, so we have our grams now. We've converted from kilograms to grams, so it wants to convert now from the grams to what? To milligrams. Okay, so we know that basically 1 gram is basically equivalent to what? To 1,000 or 10 to the power 3 milligrams. So what happens if we get to multiply that? So 0.020 multiplied by 10 to the power 3. Okay, so the value that I'm getting is basically a 20,000. So I have 20,000 milligrams. That is how you get to do your conversions. Well, convert to 875 cubic centimeters to liters. So we also need to understand the relationship between cubic centimeters to liters. So what you need to know is that 1,000 cubic centimeters is equivalent to a decimeter cubed or a liter. By the way, 1 decimeter cubed is equivalent to a liter, so we need to understand that. So if you're given 2875 cubic centimeters and you want to convert to a liter, so you know that per every liter you have 1,000 cubic centimeters. So the 2875 that we have divided by 1,000, what you're going to get is going to be your solution in what? In liters. So 2.875 what? Liters. Okay, so there we are. So what is our answer? A metallurgist is making an alloy that consists of 325 grams of chromium and 2.5 grams of iron. Find the total mass of mixture in kilogram. So we are also told notice the significant figures. So we've been given 325 grams of chromium being combined with 2.5 kilograms of what? Of iron. So we are asked to find the total mass in kilograms. So since we need our solution in kilograms, we want to convert the 325 to a kilogram. So 325 grams multiplied by a kilogram. Per every kilogram, we know that it's supposed to be 1,000 grams. So 325 divided by 1,000 gives us 0.325 kilograms. So this value that we have is supposed to be added with a 2.5 grams of iron for us to get the sum. So after adding, I'm getting a 2.825 kilograms. But we also need to put into consideration what? The number of significant figures. So what many significant figures do we have at the start of the question? We only add what? 2 there, 3 there. So it gets to consider the least number of significant figures. Okay. So therefore, our solution is just 2.8 kilograms, because we are considering the least of the smallest number of what? Significant figures, or smallest number of decimal places in terms of addition. 4. The density of lead is that. So we've been given the density to be 11.34 grams per milliliter. So calculate the density in kilogram per liter. So we will have to convert each unit that is part of this step by step. We do understand that per every kilogram we have what? 1,000 what? 1,000 grams. So for us to convert that grams to kilograms, we have to multiply by what? We have to multiply by a kilogram, then divide by 1,000, so that the grams can cancel out. Then now we know that a milliliter, every liter has got what? 1,000 milliliters. So it wants to do away with the milliliters, okay, over what? A liter, so that our units can stand out. So the milliliter will cancel out, our grams will cancel out, so that on our units that are going to stand out will just be what? Will just be kilogram per liter. So we're just going to have 11.34 kilogram per what? Per liter. So basically, among the options that we have, there is no solution to our question. So basically, what you need to understand is 1 gram per milliliter is basically in the ratio of, it's the same kilogram per liter. And I've just shown you how to go about it, just in case you're given something different that may not be in the ratio of 1 to 1. But for the sake of this question, basically the answer still remains the same. What changes are the units. Okay. So now, in summary, to just help you remember the prefixes that are very applicable in terms of conversions, just know that at least the common ones. So what you need to understand is we have what we call the smallest unit that we're going to deal with is we have what we call cents, we have what we call milli, we have what we call micro, we have what we call, also have what we call a dec, then we have what we call nano. These are the common ones. Then we also have what we call kilo, then milli. So milli, excuse me, milli and micro have already been shown there. So we have a kilo, then we have a mega and a giga. These are the common ones that are going to meet. So micro is denoted by that. Milli, small letter m. Mega, capital letter M. So dec is a small letter d. So that is 10 to the power negative negative 1, 10 to the power negative 2. So all these are the raised to the power negative ones. These are the small ones. Okay. So that what this means is, if you have a meter, for example, a meter is equivalent to what? So it's going to be to 10 decimeters. So that if I multiply by 10 to the power negative 1, it will be a 1. So 1 meter is also equal to 100 centimeters. That's how we have squared there. For a milli, 1 meter is equivalent to 1,000 what? 1,000 milliliters or millimeters. You continue moving like that. 1 meter is also equivalent to a million what? Micrometers, and also a billion nanometers, just and so on and so forth. Okay. Then on the other part, these are the positive ones. So kilo is 10 to the power 3, mega is 10 to the power 6, giga is 10 to the power 9. So these ones basically require you to consider them to be smaller because they are big units. So if you have a kilometer, for example, this requires you to understand that it's basically 1,000 meters. But for these other ones, whatever unit that you're going to have, make sure that they are the ones that should have what? A bigger number, because they are small. But for these ones that are bigger, the actual unit should have a greater figure as compared to the kilo, the mega, and the giga, because they represent big digits. Okay. State the right number of significant figures. So before we get to do that, there's just simple rules that we have to understand under significant figures. We need to understand that if basically all numbers 1 to 9 are significant, irrespective of what? Their position. They are all going to be significant. But then the rules basically gets to be more strict as you get to talk about zeros. So there may be cases where you have zeros like that. There may also be a case where you have zeros in between numbers. There also may be a case where you have zeros that are preceding, like that. Okay. So we have a lot of things that we can talk about. So how many significant figures do we have? So to start with, zeros after a decimal point are considered to be what? Are considered to be significant. Zeros in between numbers are significant. Zeros before digits like this, all these are not. They are not significant. In between, they are significant figures. These are major rules that we have to understand on the significant figures. Okay. So for the first one, how many significant figures do we have? So we only have 2 significant figures. We're only considering 4 and 5. Zeros after the numbers are not significant whenever there is no decimal point. Then this one, the zeros, they are also not significant, but we have 3 significant figures, because the 0 at the end is after a point, is on the right hand side of a point, and after a number. Okay, so now the very good part I like about this is most of the people get to be confused in a case where you have this kind of an expression, and in a case where you have 20.0. Maybe let me also put 22.0. So how many significant figures do we have in 2.0? There are 2 significant figures. 20.0, 2 significant figures. 22.0, 3 significant figures. So now the question is how? Zeros that come after a number, after a decimal point, they are significant. When a 0 that comes after a decimal point, but when there's a 0 there, it's not significant. So this one is not significant. So we only have 2. Here, this 0 is coming after a certain number there, so, and it's after a decimal point, so 3 significant figures. Very important to understand that. 0.045, so we have 2 significant figures there. Okay, so that is how you get to look at the significant figures. So now there's some rules that apply to addition of decimal numbers. So for addition and subtraction, the rules are: after adding 2 numbers, consider what? Consider the least number of what? Decimal places. That is the way it works. So if you have, for example, in the first case where you have got those 2 different numbers, go for the one with the least number of decimal places. Okay, so if you get to do addition there, 35.6 plus 56.27. What I'm getting is basically 91.87. So now looking at this number of decimal places there, we only have what? We only have the least number of decimal places is a 1. Here we have 2 decimal places. So we only want to consider a 1 decimal place here. So if we do that, we're going to have what? We're going to have 91.9. The other part, the same concept applies. Here we have 3 decimal places. Here we have 4. So we'll go for the 3 is the least number of what? Decimal places that we have. Okay, so I'm getting 89.0498. So going for the least 3. So 89.0498. So only 3 decimal places. 1, 2, 3. So get a 1 there. It's gonna be a 0 there. So I have 89 point. So the one that we're going to add to the 9 is going to make it a 10. So the one will go to the next number 5. So that becomes our solution. Then the other one, 6.2 plus 4.114. I'm getting a 10.314. Least number of decimal places, 1. So our answer is just 10.3. The other one, 7.331 plus 12.42. What we have? We have 19.751. The least number of decimal places there is what? You have 2, 3, so 2. So our answer is 19.75 as it is. We ignore the 1. Then for the last one, we have 4 decimal places. We have 2, 3. So we'll go for 2. So 22.5285 plus 22.14 plus 4.266. So 48.9345. The list's 2. So 48.93. That is how you get to look at the addition and subtraction of decimal numbers, decimal or decimals. Question 4. We are required to convert from miles to centimeters. How do we get to do that? How do we get to convert from miles to centimeters? Okay, so there's some conversions that are very helpful in our calculations. There are just a few things that we have to put in mind in terms of conversions. So what do we know? At least we know that we can't convert directly unless otherwise. You can't convert direct to miles, from miles to centimeters, but at least we're able to move to feet. At least we know that basically a mile is equivalent to what? To 5,280 feet. Then we also know that basically 30.5 centimeters is equivalent to what? To 1 feet. So if we can convert the miles to feet, and then so what do we have? So our 150 miles to start with. So I want to do away with the miles. So I multiply by 5,280 feet per mile, so that the miles can cancel out. Then we also know that we're interested more in centimeters. and we're not interested in the feet there. So that the mouse can divide, the feet can cancel out, so that you just remain with centimeters as well. So grab your calculator, 150 multiply by 5280 multiply by 30.5. Multiply by 5280 multiply by 30.5. So I'm getting 24,156,000. That is the value that I'm getting in centimeters, which is a very, very big value. Okay. Going to the other one, which is requiring us to move from gallons to cubic centimeters. There are also a few things that we have to understand there. At least we know that 1 gallon is basically equivalent to what? It's equivalent to 3785.41 cubic centimeters. So since that's what we know, and we've been given 12.1 gallons, so I can count that. So I want to deal with a gallon, so multiply by 1 over gallon, and each gallon is basically equivalent to 3785.41 cubic centimeters. So that this can cancel out, and the ultimate should remain with 2.4 times 10 to the power 7 what? Cubic centimeters. Converts milligrams to microgram. Okay, so at least I know that 1 gram is equivalent to 1,000 milligrams. So if you have a single milligram, if you have a gram or a milligram, to convert it to grams, I can multiply by what? 1 gram, 1,000 what? Milligrams. So I've converted to grams, but I also know that in a gram there are what? So we said in a gram there are 1,000. So a million micrograms or milligrams. So converts milligrams to microgram. So yeah, so we now know, we also know that we have 10 to the power 6 micrograms. Okay, so for micro we don't even get to use the symbol that I'm indicating there, so we basically get to say micrograms, so over a gram. So ultimately, the direct ratio that you need to know is 1 milligram is basically equivalent to 1,000 what? Micrograms. That is also fine. So therefore, our solution is going to be 1 by 10 to the power 3 micrograms. That is the way you need to look at that. Question 5. Comment on the accuracy, precision, and combination of both in the 3 learns carried out using 3 different dispensers. Suppose a quality control chemist at a pharmaceutical company is tasked with checking the accuracy and precision of 3 different machines that are meant to dispense 10 ounces or 296 milliliters of cough syrup in 2 storage bottles. She proceeds to use each machine to fill 5 bottles and then carefully determines the actual volume dispensed, obtaining the results tabulated in the table. Okay, So we've been given all these different results. We're just supposed to comment in terms of accuracy and precision. So with accuracy, we basically get to look at how closer the values are to the actual value. Okay. Then for precision, it depends on the values that you've gotten. Compare them. Are they closer to each other? Okay, so I'll start with the dispenser one. We have 283.3, 284.1, 283.9, 284.0, 284.1. Are they closer to each other? Or they are different? So look at 283.3, 284.1, 283.9, 284.0, 284.1. Are they closer to each other to start with? Or maybe they are not. So basically they are closer to each other if you look at how they are. Okay, you have a 4, you have a 4, you have a 3, 3.9, which is almost a 4, 4.1, 3.3, not bad. Dispenser 2, 298.3, 294.2, 296. So these basically are actually not very close as compared to the first dispenser. They are somehow far apart from each other. So you have a 4 there, 8, 6, 7, 3. So they are different. For the dispenser, the third one, 6, 5, 6, 6. So these are very precise. They are very closer to each other. So they are very precise. Then in terms of accuracy, we need to compare the values that we have in respect to the actual one, which is 296 milliliters. So they are also accurate because they are closer to that value. Then these, they are not precise as they are not closer to each other. They are not accurate because they are far from the actual value there. These ones are precise because they are closer to each other, but they are not what? They are not accurate because they are not closer to the actual value. So accuracy basically gets to compare your determined results with the actual or the true measure. But then for preciseness, basically you get to compare the various results or measurements that you take. If they are closer to each other, they are said to be precise. Express in exponential notation and also correct number of significant figures. So in exponential notation, basically you want to show the powers there, and you get to look at a decimal place. So 704. So whenever you have a number, what you need to understand is that there is a decimal number at the end there. So it's going to be 1, 2. So we have 7.04 by 10 to the power. How many times have we moved? 1, 2. So that's what we have. We've expressed our first one in exponential notation. For B, let's move a decimal point to somewhere there. So basically for exponential notation or scientific notation, we get to move a decimal point at least a digit before. A digit, a number between 1 and 9 is supposed to come before a point. It's supposed to be on the left. So we want to move that. So how many times are we going to move? Remember we have 0.007157. So let's get to count. 1, 2, 3. So we have 7.157 times 10 to the power negative 3. 7.157 times 10 to the power negative 3. So why negative? Because the number is basically small. We are moving from the left to the right. Unless if we are moving from the right to the left, that's when we get to put a positive power. And this other one, How are we going to move? So 1, 2, 3. One point zero zero times 10th part times 10th power. How many times have we moved? 1, 2, 3. Okay, so that is how you get to take to exponential notation, or scientific notation, or exponential notation. It's very, very simple. True or false? The number of eggs in a basket is exact. The number of millimeters in a centimeter is uncertain. The 0.8 as one significant figure. So the number of eggs in a basket is exact. Can you know the number of eggs in a basket? Yes, you can. It's determinable. So it's true. B. The number of millimeters in a centimeter is uncertain. Is it true? Don't we know the number of millimeters in a centimeter? The number of millimeters in a centimeter is uncertain. So basically, if you look at a centimeter, for example, if you look at 2.7 centimeters, so the uncertainty applies to this value that is at the end, which is millimeters. So that is also true. We are uncertain of the millimeters that may be in a centimeter. 0.8 as one significant figure. True. 0.008 as two significant figures. No. False. 0.008 as one significant figures. True. Okay. That is basically what you need to understand. Perform the following calculations and report the correct number of significant figures. So, just like we talked about the issue of addition and subtraction, for addition and subtraction we said, basically you get to look at the least number of decimal places. But on the other hand, for addition, for multiplication, and division, we get to look at the least number of decimal places. So if you look at the first one there, the least number of significant figures, so here we are looking at the least number of significant figures that you have. So if you look at the first one, 5.63 by 10 to the power 2 being multiplied by 7.4 times 10 to the power 3. The least number of significant figures are in which number? They're in 7.4. There are only 2. Here there are 3. So we're going to multiply 5.63 multiplied by 7.4. I'm getting a 41.662 times 10 to the power 5. Now the least number of significant figures is supposed to be 2. So our answer can be 42 times 10 to the power 5. That's very much okay. For the other one, where we have 28 divided by 13.483, 2.076689. Least number of significant figures 3, 5. So 3, 1, 2. So 2.08. Assign the correct oxidation number in the individual atom or ion below. So there are some rules basically that gets applied to the issue of oxidation numbers. If you've not watched our tutorial on that, do well to check it out. Okay. So how do you get to assign the oxidation numbers? So there are some few things that basically are known that you're supposed to take down for the oxidation numbers. So for oxygen, the oxidation number is 2 minus. For hydrogen, it's a positive 1 in non-metals and a negative 1 in metals. But usually for most of our calculations, we get to consider it to be positive. Group 1 metals have a positive 1. Group 2 metals, a 2. So group 6, where oxygen is coming from, we basically get to consider them to have a 2 minus, just like oxygen. Okay. So what you need to understand is that basically the ones that are in between now are the ones that have got problems with the transition elements. Basically are the ones that exist as isotopes. So they get to have differing oxidation numbers. So if you look at the first one, for example, we have that. So for oxygen, we know it's determinable. It's what? It's a 2 minus. So the negative 2 is what I'm going to multiply by the number of atoms present, which are 2. For the manganese, we don't know. So now the addition of the 2 is supposed to give us what? 0, because that is the overall charge of what? The compound. So I have negative 4 plus x being equal to 0. So my x is what? A positive. So in the first compound, manganese, it's a positive 4. Oxygen, it's a minus 2. Moving on to the second part, we have iodine what? 3 minus. So basically the 3 is not basically the power, it's a 3 on the bottom, then a negative 1 as what? As the charge. So for oxygen it is determinable. So for iodine we are going to put x because we don't know. For oxygen we are saying that 3. So each has a negative 2. The overall charge of a compound is a negative 1. So we have x minus 6 being equal to negative 1. Our x is positive 6 minus 1, which is positive what? Which is positive 5. Okay. So we have a positive 5 for that. Iodine, positive 5. Oxygen still stands to be a minus 2. The third one, we need to determine for carbon. So we have hydrogen carbonate. So hydrogen plus 1. Carbon we don't know, put x. Oxygen we know it's a negative 2. We'll do our calculations. How many atoms of hydrogen do we have? We have 1. Carbon we have 1. Oxygen we have 3. So we're going to multiply the negative 2 by 3, equated to the total of the overall charge, which in this case is what? A negative 1. So our x is going to be, we have a negative 1 on the left. 3 multiplied by negative 2 is a minus 6. A minus 6 plus a 1 is going to be what? A minus 5. If it goes the other side, it will be a positive 5, which is going to be a positive 4. So for carbon, it's a positive 4 in this compound. Moving, we are on number 4 now. We are talking about the ion. We're interested in the ion now. Okay. So for such a question, basically, what this means is, of course, we do understand that S4 has got a charge of what? A 2 minus. So this ion that we're talking about in this case, if we take back that, it had what? A 3 plus. And that is how you get to come up with a formula. Just get to exchange the charges. So we've already determined even the oxidation number of it. So oxidation number in such a case is what? Was just say 3 plus a plus 3. If you want to do it, you can also do your calculations by saying, you know, You don't know for that, so 2x. But you know what is in the brackets has got a charge of a 2 minus. 2 minus multiplied by the 3 should be equal to 0. 2x is going to be equal to a positive 6. X is what? A positive 3. That is for the ion. Number 5. You have to determine the oxidation number for the oxygen. So for sodium, we basically know it's a positive 1. Oxygen, we don't know. So we have 2 times positive 1. Oxygen, we don't know. So put x, 2x should be equal to 0. So what do we have? So doing our calculations here, this goes the other side. We're going to have 2x being equal to a negative 2. Our x is equal to negative 1. So for oxygen, their oxidation number is what? Is a negative 1. Finally, in S8, do we know anything there? We don't know. So the overall charge is a 0. So if we have 8x being equal to 0, our x is equal to 0. So oxidation number of sulfur is 0. So all neutral atoms, I've got an oxidation number of what? I've got an oxidation number of a 0. Question 10. We're trying to practice how we get to name the compounds. So you have copper there attached to a chloride. So basically, using the basic idea of the oxidation numbers, if you look at what we have copper and a chloride. So a chloride basically has a charge of a negative 1. So since these guys are in the ratio of 1 to 1, it tells us to say that we have copper 1 and a chloride, because basically you get to exchange their powers. So 1 and 1, that's why they're in the ratio of 1 to 1. So why am I trying to emphasize on the idea of copper 1? Because there's also copper 2. Copper 2 plus, when it combines with a chloride, it becomes copper chloride. The chloride is supposed to have a subscript of 2 coming from there. But in this case, we're in the ratio of 1 to 1. So it's basically copper what? Copper 1 chloride as what? The name. So make sure you write it properly as you present it. Okay. Don't just say copper chloride, specify, is it copper 1 or copper 2? Then the other one, we have magnesium attached to the hydroxide. So it's just magnesium hydroxide. Okay, why magnesium hydroxide? Why can't we say magnesium 1 or magnesium 2? So for metals like magnesium, group 1 and group 2 metals, we basically understand, we know that they don't have isotopes. So it's just magnesium hydroxide. Doesn't require you to say anything, just say magnesium hydroxide, that's enough. Then for the last part, in terms of naming the given compounds, we have copper, a subscript of 3, and that. So what is the name? So arsenide basically has got, if you check a periodic table, you're going to see that it has got a charge of what? A 3. So it has got 3 there. So now, if it has got a 3 and there's a 1 there, means that we're dealing with copper 1. So the name of that one is copper 1 arsenide. If it was copper 2, would have had the subscript of 2 down there. Okay, so that is how you get to look at the issue of naming. Now, Question 11 is basically the opposite of what we're from doing. Here now they've given us the names and they expect us to come up with what? The formulas. The first one is strontium chloride. What is it? What is strontium chloride? So if you go to your periodic table, strontium has got that formula. Then we have a chloride. Okay. So now, if you get to look at your periodic table, where basically do you get to find strontium? So you're going to notice that strontium is basically in what? Is basically in group 2. Chloride is in group 7. So those are their charges. So coming up with a formula is going to be strontium chloride 2. So basically we get to exchange. So a negative 1 we get considered to be a 1. So that is how you come up with a formula. You exchange their charges. Part 2, titanium iodide. How do you get to come up with a name there? So if you go to your periodic table, you're going to notice that basically your iodine is in group what? Is basically in group 7 as well. So which tells us that it has got a negative 1 as a charge. Then how do you get to locate titanium? So titanium is one of the transition elements. So basically the charge of titanium is a positive 4. So coming up with a formula is titanium iodide what? 4. Moving on to the third one. So just for own information, titanium may have different charges, but the question has specified titanium 4. So it's Ti with 4. Then iodine, it's known it's a negative 1. And that's how we're coming up with a formula. It's not like you just have to master, no. The question is specifying titanium 4 because transition elements may have varying what? Varying charges. Now we are now on the iron 3 oxides. Iron 3. So we've specified because there's also iron 2. So we've specified iron 3. Iron 3 then with the oxides, which is a 2 minus. So if you get to come up with a formula there, it's going to be that will come here, then that will go where there's oxygen there. So that is how we come up with the iron 3 oxide formula. Then finally we have cobalt 2 nitrate. So cobalt, that's the formula. So we've said cobalt 2, so it has got a charge of 2. Then a nitrogen, of course, a nitrate. We do understand that it's what? Nitrogen is in group 5. So it requires to lose what? Or to gain 3 electrons for it to be stable. So if you get to exchange the 2, you're going to have cobalt 3 and what? And 2 if you exchange their charges. And this is the formula for the what? For the cobalt 2 nitrate. Okay, so this is what we had to talk about in this video. Thank you very much for watching to the end. I just hope that you now understand how to approach questions in chemistry, and you've reviewed how to do your conversions and also how to deal with your significant figures.